Intro music. Ethereal cosmic soundtrack fades in. Are we destined to remain forever tethered to our home planet? Or will humanity one day dance among distant stars? The cosmos beckons with its infinite mysteries, but the vast, cold vacuum between celestial bodies presents challenges that defy our current technological grasp. Yet, throughout human history, what once seemed impossible has repeatedly yielded to human ingenuity. Today, we stand at the precipice of a new era in space exploration, one that could transform us from a single-planet species to voyagers of the cosmic ocean. Welcome to Future of Space Travel, where we'll journey through the enigmatic possibilities awaiting humanity beyond Earth's atmosphere. I'm Dr. Eliza Cosmos, and this is Unusual Science. Before we launch into tomorrow's possibilities, let's briefly examine where we stand today. Our current space travel technologies remain fundamentally similar to those that first carried humans to the moon over half a century ago. Chemical rockets, powerful but inefficient, remain our primary means of escaping Earth's gravity well. The International Space Station orbits just 400 kilometers above our heads, merely 1,000th the distance to the moon. With current technology, Mars journeys would take 7 to 9 months one way, exposing astronauts to dangerous radiation and microgravity effects. Venus, 5 months. Jupiter, over 2 years. And venturing beyond our solar system? At conventional speeds, reaching even the nearest star would take tens of thousands of years. Yet beneath these sobering realities stirs a renaissance of space innovation that promises to shatter these limitations. The landscape of space exploration has been transformed by the emergence of commercial space entities. Companies like SpaceX, Blue Origin, and others have dramatically reduced launch costs through reusable rocket technology. What once cost $54,500 per kilogram to launch into orbit during the Space Shuttle era now costs under $2,700. A 95% reduction that has democratized access to space. This economic revolution underpins everything we'll discuss today. For as the financial barriers to space collapse, possibilities once confined to science fiction begin manifesting in engineering blueprints. Let's embark on our journey through the future of space travel by examining the near-horizon developments likely to materialize within the next 2 decades. Most imminent is humanity's return to the moon through NASA's Artemis program and the Lunar Gateway, an orbiting outpost that will serve as a staging point for lunar surface operations. Unlike the Apollo era's brief sojourns, these missions aim to establish a permanent human presence on our celestial neighbor. Advanced life support systems, 3D printed habitats utilizing lunar regolith, and water ice mining from permanently shadowed craters will transform the moon into humanity's first off-world outpost. Meanwhile, Mars beckons. The 2030s will likely witness the first human footprints on the red planet. These initial missions will be reconnaissance expeditions rather than permanent settlements, but they'll develop and test technologies essential for eventual colonization. Propelling these ambitious plans are revolutionary advances in spacecraft propulsion. Ion thrusters, which use electrical fields to accelerate charged particles, offer fuel efficiencies 10 times greater than chemical rockets. While their thrust is minimal, their ability to operate continuously for years enables spacecraft to eventually reach tremendous velocities. NASA's next ion thruster technology can maintain continuous thrust for over 48,000 hours. That's 5.5 years of uninterrupted operation. For comparison, the Space Shuttle's main engines operated for just 8.5 minutes during a typical launch. Solar sails, gossamer-thin reflective membranes spanning hundreds of square meters, harness the gentle but constant pressure of sunlight to achieve acceleration without consuming any propellant whatsoever. Japan's IKAROS mission has already demonstrated this technology's viability. The accessibility of space is undergoing a profound democratization. Virgin Galactic and Blue Origin have inaugurated suborbital tourism, while SpaceX's Polaris Dawn mission aims to conduct the first commercial spacewalk. Orbital hotels are progressing from conceptual designs to actual construction plans. Axiom Space is developing modules that will first attach to the International Space Station, before eventually becoming an independent commercial space station. The booming CubeSat industry has placed space research within reach of universities and even high schools. These miniaturized satellites, often no larger than a shoebox, cost a fraction of traditional satellites, yet perform sophisticated science and Earth observation missions. As we venture farther into the century, more transformative technologies emerge. Nuclear propulsion systems, both nuclear thermal and nuclear electric, offer a quantum leap in capabilities. A nuclear thermal rocket could reduce travel time to Mars from 9 months to just 3, dramatically decreasing radiation exposure and psychological challenges for astronauts. NASA and DARPA's Draco project aims to demonstrate nuclear thermal propulsion in orbit by the early 2030s. Meanwhile, NASA's Kilopower project is developing small fission reactors that could provide reliable power for lunar and Martian outposts regardless of local conditions, enabling settlements in permanently shadowed craters or during planet-wide dust storms. By mid-century, lunar development will have progressed from outposts to actual colonies. Helium-3 mining, harvesting an isotope rare on Earth but relatively abundant in lunar regolith, may provide fuel for future fusion reactors. Lunar observatories on the far side, shielded from Earth's electromagnetic noise, will peer deeper into the cosmos than ever before. Mars settlements will likely begin as scientific bases before gradually evolving toward self-sufficiency. The greatest challenge will be psychological creating environments where humans can thrive, not merely survive, millions of kilometers from Earth. Virtual reality connections to loved ones, carefully designed social structures, and enclosed ecosystems mimicking Earth's biomes may help address the profound isolation of Mars colonists. Asteroid mining represents perhaps the most revolutionary economic development in human history. A single 500-meter metallic asteroid could contain more platinum group metals than have ever been mined throughout Earth's history, potentially worth trillions of dollars. Beyond precious metals, asteroids offer something even more valuable for space development: water. Water can be split into hydrogen and oxygen for rocket fuel, used for radiation shielding, and of course, sustain human life. Asteroid-derived resources could enable construction of massive structures in space without the enormous cost of launching materials from Earth's deep gravity well. Companies like Astroforge are already planning initial asteroid prospecting missions in the 2020s, with actual resource extraction potentially beginning in the 2030s. Perhaps the most tantalizing mid-century development would be breakthrough launch technologies that eliminate rockets entirely. Space elevators, ultra-strong cables extending from Earth's surface to geosynchronous orbit, could reduce launch costs by 99%, but require carbon nanotube materials several times stronger than anything currently manufacturable. More viable in the shorter term are star tram-type launch loops, magnetically levitated tracks that accelerate spacecraft horizontally before curving upward through mountain ranges and sending payloads into orbit. Though requiring substantial initial investment, such systems could eventually launch payloads at $40 per kilogram, less than 1% of current costs. Venturing into the latter part of the century and beyond, we confront the greatest challenge: interstellar travel. The distances are mind-boggling. Proxima Centauri, our nearest stellar neighbor, lies 4.2 light-years away. At the space shuttle's maximum velocity, reaching it would take 73,000 years. Yet theoretical propulsion concepts offer glimpses of possibility. Breakthrough Starshot proposes using gigawatt lasers to accelerate gram-scale spacecraft to 20% light speed, reaching Alpha Centauri in just 20 years. Though only capable of carrying miniaturized instruments, such probes could beam back the first close-up images of an exoplanetary system. For human interstellar travel, more exotic approaches may be necessary. Fusion rockets could theoretically achieve 10% light speed, while antimatter propulsion, though currently prohibitively expensive to produce in significant quantities, could approach 30% light speed. If faster-than-light travel proves permanently unattainable, as Einstein's theories suggest, humans might still spread to other stars through generation, ships, self-contained worldlets where multiple generations live and die during journeys lasting centuries. Alternatively, suspended animation technologies might allow travelers to effectively skip forward through time during long voyages. Researchers have already achieved hibernation-like states in non-hibernating mammals by manipulating hydrogen sulfide levels, suggesting human hibernation may not be merely science fiction. The most efficient approach might be sending advanced 3D printing technology and synthetic biology capabilities, along with genetic templates for human embryos, allowing AI systems to birth and raise human colonies upon arrival at suitable planets. As we contemplate these possibilities, profound challenges and ethical questions emerge. The economic case for space development must be compelling enough to sustain multi-decade investments. International legal frameworks must evolve to address questions of resource rights, planetary protection, and sovereignty in space. The environmental ethics of altering other worlds demand careful consideration. Should we terraform Mars if it contains indigenous microbial life? Do we have the right to remake other planets in Earth's image? And what of the social and political structures of space settlements? Will they repeat Earth's mistakes or pioneer new forms of human organization? Yet beneath these challenges lies an inescapable reality. Earth is the only world currently known to harbor life, and it exists in a cosmic shooting gallery of asteroids and comets. The mathematical certainty of eventual extinction-level impacts makes spreading beyond Earth not merely an adventure, but perhaps an existential imperative. As author Charles Cockell observed, once life escapes Earth's surface, its future survival is independent of the Earth. If the Earth were to disappear tomorrow, life on the Moon or Mars would continue. The technologies we've explored today represent not merely humanity's reach for new frontiers, but potentially the seeds of life spread throughout a sterile cosmos. Perhaps that more than resources, scientific knowledge, or adventure is the deepest purpose of space exploration. As we conclude our journey through the future of space travel, I leave you with a thought both humbling and inspiring. Look at your hand. The atoms comprising it were forged in stellar crucibles billions of years ago. In a very real sense, we are already stardust. Perhaps our destiny is to return to the stars not as visitors, but as bringers of life, consciousness, and wonder to a universe that seeks to know itself through us. The road to the stars is long and fraught with challenges, but with each passing year, it becomes less science fiction and more science future. The question is no longer if humans will travel among the stars, but when and what we will become in the process. Thank you for joining me on this cosmic journey. I'm Dr. Eliza Cosmos, and until next time, keep looking up. Outro music, ethereal cosmic soundtrack fades out.